Okay, we're continuing our work in Unit 8. Now we're looking at Lesson 2. Lesson 2 is all about the Cartesian equation of a line in R2. Just so that there is no confusion, because we've been talking about vector and parametric equations, so vector and parametric equations will be written using a parameter t. A Cartesian equation will be written using the variables x and y, which are the variables found in the Cartesian plane. So what we're going to do today is take a different look at the Cartesian equation of a line, shed some new light on it for you. So we'll start with, we did learn in the previous lesson that the vector equation of a line, we need a point, we need a direction vector. There's the point vector, here's the direction vector. The parameter t now will trace out all points of the line, and we do need to include that t is all real numbers. Now, what's the Cartesian equation? So the first thing you're going to have to do is tell me what the slope is. So based on this particular direction vector, this is the x component, that's the y component. But we remember, of course, a slope is delta y over delta x. And remember, this really does describe a change in x and its corresponding change in y. So the slope, of course, should be 2/3. What's the point that's on the line? Well, we do know that that's the point on the line. So the point -3, 1 is on the line. Now, to go to the equation, we can go straight to the equation of the line using point-slope form as outlined in our calculus. This is the vectors component, but in the calculus component, we're doing derivatives and we're finding the equation of the tangent line. I'm going to show you something alternately here. This is really the definition of slope, and that's where the point-slope form comes from. This is any point on the line. So if I want to find the slope of this particular line, I just find delta y between a point on the line, and this is a general point on the line, and a known point on the line. So our known point on the line has y coordinate 1 and x coordinate -3. So y minus 1 divided by x take away -3 should always give me the slope back. That's where a point slope form comes from. And of course, we're used to just having the 3 over here, and we're used to saying y minus 1 equals 2/3 times x plus 3. That would be the Cartesian equation of the line in point slope form, but what I'm going to try to do is move this to slope y-intercept form so that we can pick off the slope. So 3y minus 3 equals 2x plus 6 if I expand. 3y equals 2x, 3 plus 6 is 9. Then divide by 3, I'm going to get y is 2/3 x plus 9 over 3. That gives me y is 2/3 x plus 3, and of course this would be the y-intercept. So this is a Cartesian equation of the line. This one is written in slope y-intercept, and this is the form you're probably familiar with. If I give you a Cartesian equation of a line in this form, then what I would like you to do is tell me what its vector and parametric equations are. So the first thing we're going to have to do is we're going to have to use, to find the vector and parametrics, be clear, we need a point and we need a direction vector. So we're going to have to use the slope here to give us the direction vector. So the slope is 5/2, and remember a direction vector, and remember what a slope does, it describes a change, right? If the x coordinate changes by 2, then the corresponding y coordinate has changed by 5, and that's really what a vector does. So, but when we write it in vector form, we do the x component first, so the 2 will come first, comma 5. There's the direction vector. We need a point on the line. Well, they did tell us that the y-intercept was -8, and of course that means the point 0, -8 is on the line. So when we go to our vector equation, we're going to have r equals, and then we should have our point vector followed by the parameter times our direction vector, and then we should note that our parameter can be all real numbers. So there is our vector equation. R equals 0, -8 plus t, 2, 5. T is any real number. Parametrically, we're going to grab 0 plus 2t for the x component. We'll have -8 plus 5t for the y component. So there are our parametric equations. And then we should just note, of course, that t is any real number. So we can go back and forth from vector and Cartesian. We've talked about the direction of a line can be described either by its slope or a direction vector. And when we think about a direction vector, remember we're imagining that this tail is going to be pulled back to the origin, and then the tip will move correspondingly. So I'm going to have to subtract x naught from this, and I'm going to have to subtract y naught from that. But notice when we go to find the slope of a line, what we do is to find delta x, we subtract the x coordinates. To find delta y, we subtract the y coordinates. So we do know the slope would be y1 minus y naught divided by x1 minus x naught. The direction vector would be x1 minus x naught, comma, y1 minus y naught. Now, summarizing, so if we have a direction vector of a line being a comma b, then we know that corresponds to a slope of b over a. If a is 0, then the line's vertical. The slope would be undefined, but the nice thing about the vector equation of a line, of course, is that the direction vector can be defined. When the slope of a line is undefined, we would have 0, comma 1. So 0, comma 1 would be right here. So you can see we would be the y-axis vector, thus giving us the vertical line. All right, now I'm going to show you an alternative Cartesian form of a line, and I want to talk about normals. So we're going to start with line capital L. It's a general line in R2. There's only one line that I can draw through that. So here's my L, capital L right there. There's only one line that I can draw through that would be perpendicular to it, that passes through the origin. So from the origin to this line being perpendicular, there's only one line I can draw. This would be called the normal axis. And again, a normal itself, so the line that's passing through there is the normal axis, but the normal itself could be created by joining the origin to any point on this particular normal axis. So I'm going to note that the normal could be written as a comma b. Where a comma b is any point on the normal axis. Now, p naught is the point, the given point that we would need to be on the line, and pxy is a general point, any point on the line. And remember before we had that green vector coming from here. We took any scalar multiple of our direction vector, we added that to that, and that's how we traced out the points in the line. So this is our known point. This is any point on the line. And so the vector p naught p could be described this way. Imagine translating this back to the origin, we would do x minus x naught, y minus y naught. So I now have these two vectors. But the interesting thing about these two vectors is we do know that they are perpendicular. That means their dot product is 0. So again, I'm just going to recap where these came from. AB is any point on the normal vector. The tail is at the origin, and the tip is at AB. So as a vector, I can write the normal as a comma b. Right now, p naught and p are 2 points on this line, so if I want a vector to represent that line, I'm going to have to write it as p naught p, and that would be x minus x naught, comma y minus y naught. And now I'm pointing out that since they're perpendicular, their dot product is 0. So a comma b dotted with x minus x naught, comma y minus y naught would be 0. And so remember how dot product works. I need to do a times in brackets x minus x naught plus b times in brackets y minus y naught needs to be 0. Expanding, I get ax minus ax naught plus by minus by naught. Grouping things that are like x and y are general points on that line, so I'm going to group them together. Ax plus by naught minus ax naught minus by naught. Now the thing we have to remember now is this and this. They're unknown constants, right? That's a given point on the line. It's a known point on the line. These are constant values, whereas the points x, y is a general point on the line, so we're seeing these as variables that can change. So what does that mean? That means minus ax naught minus by naught is just a constant. It's an unknown constant. So what I'm going to do is I'm going to replace this with the letter C. minus ax naught plus y naught I'm going to replace with plus c. And that gets me to this equation here. So this is a Cartesian equation of the line, but in this particular form we now know, I mean, when you use this form in grade 9, I think we call this standard form equation of a line. So we have ax squared plus bx plus c equals 0. We call that the standard form equation of a quadratic, and the standard form equation of a line was capital AX plus BY plus C is 0. What we didn't tell you in grade 9, of course, was that the A and B are representative of the normal to the line. They give you the direction of the normal vector. So moving to our next slide, this is our big summary now. This is our new learning in terms of a different view of the Cartesian equation of the line. So in R2, we are now not going to be thinking about slope y-intercept form. We're going to be thinking about the Cartesian or scalar equation as this: ax plus by plus c equals 0, where a normal to this line is given by the normal vector a comma b. And if a, that shouldn't say a, I'm going to fix that. All right, so if the direction vector of our line is b comma a, then in R2, negative a comma b would be the normal to the line. So big learning key, though, is this scalar equation or Cartesian equation of a line. In order to find that, I just need to know the normal of the line. If you didn't give me to the normal to the line and I am in R2, then I can swap the coordinates and switch the sign of one of them, and then that will give me the normal, and I can use that to create my scalar equation. All right, in terms of parallel, perpendicular, and now thinking about normals instead of direction vectors and slopes. So before, when we wanted to determine whether or not lines were parallel when we were in grade 9, we would check to see that the slopes were equal to each other. If we were thinking about direction vectors, and I know that's a new concept because we just learned that the previous lesson, but if two lines are parallel, then their direction vectors would be scalar multiples of each other. But there's another way we can think of it now. So see how these two lines are parallel to each other, L1 and L2? Their normals are also parallel to each other. So instead of checking that the direction vectors are scalar multiples of each other, what we could do is check that the normals are scalar multiples of each other. And that's one way of seeing if the lines are parallel. Now notice that L1 and L2 are perpendicular, and so too are their normals. So instead of checking direction vectors, what we can do instead now is check to see if the normals are perpendicular. And of course, in grade 9, we would check for negative reciprocals. We would know that two lines were perpendicular if we could have said the slopes, the product of the slopes of their lines is -1, or if the slopes are negative reciprocals. In calculus and vectors, what we're going to do is this right here. We are going to check to make sure the dot product of the normals are 0. All right, now we're going to move on to the next slide. Do some examples. Find the Cartesian equation of a line which passes through 5, -3, and it has a normal -2, 7. And so remember that Cartesian form of the line was ax plus by plus c equals 0, where ab was the normal. Well, you've been given a normal. And then after we've plugged that in, we should be able to use this point to find c. So let's start with the basics. Let's start with the equation. So the equation is ax plus by plus c equals 0. We do know what the normal is. We can use the normal to find our a and b values. So the normal is -2, 7. So a is -2 and b is 7. Plugging those into the equation here, I'm going to get -2x plus 7y plus c is 0. And now I need to find c. So if I'm going to find c, what I want to do is plug the point 5, -3 into this equation and then isolate for c. So I'm going to plug in a 5 for x, and I'm going to plug in a -3 for y. That gets me to here. I'm now going to have -10 minus 21, which is -31, plus c is 0. That's going to take me to there. -31 plus c is 0. So we now know that c is 31, and then plugging all of that back into here, we now have our Cartesian equation is -2x plus 7y plus 31 equals 0. That was example 1. example 2, show that those two lines are parallel and non-coincident. And I think I'm going to add to that, it will be understood on a test that you will be using techniques from calculus and vectors, and specifically for this, we'll be using vectors techniques. So if anyone were to take this and try and write it in slope and y-intercept form and compare the slopes, I might give you a 50 for that, but I'm not going to give you full credit. So because this is calculus and vectors, what we're going to use are the normals for these two lines to decide whether or not they are parallel. So the normal for the first line is 3, -4. The normal for the second line is 6, -8. So that's where we're going to start. And now we will take a look. Are these scalar multiples of each other? Because if they are scalar multiples of each other, we know the normals are parallel. And if the normals are parallel, then the lines would be parallel. So if we multiply normal 1 by 2, we will get normal 2. So since normal 2 is equal to 2 times normal 1, we do know the lines are parallel. And I suppose I could tack on the end, the lines are parallel as the normals are parallel. All right, now the next thing we have to decide is, are they coincident? We do have the correct scalar multiplier, I guess I'll say it, or the correct scalar multiple. We know it's a 2. In order to get the correct normals, I would need to multiply this by 2. So what I'm going to do now is I'm going to multiply this equation by 2 and see what happens. So when I multiply, well, I just repeated that again, so let's move forward. I'm going to multiply this by 2. And when I do, I'm going to get 6x minus 8y minus 12. Now, of course, that is not equal to this. The constants are different now. This is minus 12. That one is plus 12. So there is not going to exist any t so that if I multiply the first equation by 2, I'm never going to be able to get the second equation for it. There is no such t. Therefore, the lines are not coincident. And typically speaking, not typically, this is the way it would work. The scalar multiple that you find to make the normals the same multiple would have to make the lines the same. If it doesn't make the lines the same, then you have two parallel non-coincident lines. So that's what's happening here. Now, the next one is asking for what values of k would these two lines be perpendicular? And again, I do not want you working with the slopes. This is a calculus and vectors course. These definitely, I'm taking a look at these. These are Cartesian equations of lines, so I'm going to choose to work with normals. If they gave me the vector equations of the lines, then I could do this work with direction vectors. But Cartesian form, we're going to use the normals. So again, I'm going to take a look at what the normals are. The normal for line 1 is k, 4. The normal for line 2 is 3, -2. So let's start it there. Now, if they are perpendicular, what does that mean? Well, that means the dot product of those normals would have to be 0 again. Why? If you are perpendicular, the angle between the lines is 90, and of course, the cos of 90 is 0. So that would give us a dot product of 0. So I need n1 dot n2 to be 0. Now, n1 dot n2 is going to be k times 3 minus, or 8, because 4 times -2 is 8. So I'm going to get 3k minus 8 equals 0. And then that is going to give me that 3k is 8, or k is 8/3. All right, that brings us to the end of example 2. All right, so looking at our third example, we want to determine the acute angle that's formed at the point of intersection of these two lines. The equation of these two lines has been given to us in vector form rather than Cartesian. If it was given in Cartesian form, I would be working with the normals rather than the direction vectors. Now, how do we find the angle between two lines? We can find the angle between the direction vectors. If I find the angle between the direction vectors, because the direction vectors are parallel to the lines, the angle between the direction vectors will be the same as the angle between the lines. Now, how do you find the angle formed by the intersection of two vectors? I'm not sure if you remember that, but I do have a GSP sketch open from an older lesson. We could use this rearranged formula for the dot product. The definition of the dot product was cos A times mag A mag B. However, there's an algebraic way to calculate the dot product, so we can simply isolate the dot product formula for the cosine of theta and use this particular formula here to find the angle between the two vectors. So the first thing we're going to do is I'm going to note what the direction vectors are. So the direction vector for the first line is negative 3, 5. The direction vector for the second line is 2, 3. I guess what I should note, of course, these are not parallel because there's no scalar multiples that would make them parallel. Because if they were parallel, we would not be able to find the angle between the two lines unless we wanted to say the angle was 0 or 180. So what we're going to do is going to use the formula that I just showed you. I'm noting n. Let me just make a correction there because I don't want to use n. N's a direction vector. I should be using m. Or sorry, n's a normal. I should be using m. Let me fix. All right, so because these equations were given in vector form, we're not using normals. We're using the direction vector, so I had inadvertently typed the letter n there. These should be m for direction vectors. So we're using this formula to find the dot product. It's negative 3 times 2, 5 times 3. To find the magnitude of the vector, it would be the square root of negative 3 all squared plus 5 squared. And then for the second one, it would be the square root of 2 squared plus 3 all squared, as I've shown you before, as I've shown you below. So if we simplify this, we get negative 6 plus 15, which is 9. We're going to get 25 plus 9, which is 34. And of course, 4 plus 9 is 13. So I now have that cos of theta would be 9. Divided by the square root of 34 times 13. 34 times 13 is 442. So I could now note that theta is the inverse cosine of 9 over the square root of 442. And we punch that into our calculator. I'm going to round to the nearest hundredth. I'm going to get 64.65 degrees would be the measure of angle theta. What we're going to do next is I would like to compare and contrast what we've learned. We've learned the vector equation of a line, and we've learned the Cartesian equation of a line. All right, so in the Cartesian equation of a line, there it is down here in slope and y-intercept form. Here it is in standard form. We now know in standard form that the normal would be 1, negative 2. The slope is 1/2, and notice as a vector, this would be 2, 1, and as a vector, this would be 1, negative 2. So we can definitely see that it is perpendicular. Now, what you are used to is in the Cartesian equation, you're used to picking an x, plugging it into your slope y-intercept form, and using that to find y. So you're used to the x-coordinate drives the y-coordinate. See the calculation being made over here? This x-coordinate has driven the y-coordinate. And so the y-coordinate is the dependent variable, and it's dependent on the values that I choose for x. So I'm going to show you again. X drives y. That's what you're used to seeing. But in the previous lesson, I introduced the vector equation of a line, and in the vector equation of the line, it's a bit different. We introduce a third parameter called t. Well, actually, we introduce a parameter called t, and then we're going to use it to determine the values of our variables x and y. So notice over here in this particular equation here, I now have the value of x being dependent upon the value of t, and the value of y is also dependent on the value of t. So t has driven this x calculation, and t has also driven a y calculation. So we are finding in this case that both x and y are dependent upon the value of t. And that's how we trace out all points on the line. It's worth repeating one final time. In this particular case, x is the independent variable. The value of x drives y. So x independent, y depends on whatever value I choose for x. In the parametric equation of a line, the parameter t is independent, and the values of x and y are both dependent upon what I choose for t. All right, so that brings us to the end of this particular lesson. And what were the big ideas for this lesson? Just going to take you back a few slides to this one here. How can we determine if lines are parallel and perpendicular? By using their normals, because we're given a Cartesian equation. We're using normals, no, not slopes. How can we determine what the Cartesian or scalar equation of a line is? We did determine that by using a normal and taking the dot product. We did that in this particular slide. The dot product, set it equal to 0, and we now determined that the Cartesian equation of the line, the A and B, actually give you the normal. And as I mentioned a few seconds ago, we will now determine if lines are parallel or perpendicular by comparing normals. All right, that brings us to the end of lesson 2. If you've made it to the end, thank you for watching. As Mr. Ciprietti says, if you're so inclined, smash that like button and subscribe. And as always, stay tuned for our next lesson, which is going to be lesson 3. And take care and stay safe.